or whatever time it is. I'm Rob, and today we'll be programming Conway's Game of Life into Blender. What is Conway's Game of Life, you ask? I'm glad you asked. Conway's Game of Life is an algorithm that dictates the behavior of cells on an infinite two-dimensional grid. Each cell has one of two states, either dead or alive. In this case, all of these cells are dead. This cell is alive. If I were to run this, start, the cell dies. Why does the cell die? Because of the algorithm. The algorithm dictates whether a cell will live or die each generation based on its neighbors. This cell, for example, as all cells do, have 8 neighbors. If a dead cell, if a dead cell is surrounded by exactly 3 living cells, then the next generation, it will come alive. So if I start this, this comes alive. The other rule being that if a living cell is surrounded by exactly 2 or 3 neighbors, then it lives on. Otherwise, it dies. So in this case, each cell is surrounded by exactly 3 neighbors. And with these 2 simple rules in place, you get fantastic patterns emerging. If I just kind of randomly set something up here, this may or may not be fantastic. I don't know. Let's start it. But yeah, as you can see, that little pattern emerges. You can get interesting things like this glider, for example. This thing will just live on indefinitely and just keep moving along in infinite space forever and ever. And that's it. That's Conway's Game of Life. Let's put it in. All right, as usual, open up a brand new Blender file, tab into that cube, and press S.5. Shrink that thing down so it only spans 1 unit. Control B to bevel, and just give it as much bevel as you want. That's as much as I want. So I'm going to tab out of there, and I am going to open up animation nodes. Good old animation nodes. The first thing I'm going to do is create a new node tree. Go to Node Tree tab, unclick Always, yes, 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 and N. First thing I want to do is I want to create a seed of cells that we can start our simulation with. So I'm going to create a grid mesh, get a mesh info, feed the mesh into here, get a 3D viewer just for debugging purposes. This shows me the grid. Move that there. Now, I want to change this grid size, but as you can see, everything stays within this size, so I need the mode to be step. Now, my grid units are all 1 and 1 apart, and I can scale this thing up and down like so, and this is what I like. I'm going to create an integer input. I'm going to feed that into the X and the Y because I personally want my width and my height to be consistent. You don't have to do this, but up to you. I'm going to keep this at 3 so that it's very simple as we are building this. I want to start by instancing this cube. Object instancer. Since this is selected, this eyedropper will grab the cube, and I want to hide the original, so I'm going to click this. So now there are 0 instances of the cube, nothing is showing, but if I put this vertices in here, these 9 vertices are going to create 9 cubes right here. They're all in the same spot, so you can't see them all. I'm going to create a transforms output that controls the location. Feed the cubes in and give it the vertices. And now each cube is on one of the vertices. Beautiful. Good start, but not a great seed. I want like a random selection of these vertices to start off our simulation. Get a random Boolean. Grab a viewer for debugging purposes. Feed that in there, and false. If I change the seed, I get a different random Boolean. But I don't want just one random Boolean, I want a list of random Booleans. Plug that in there, and now I get a list of randoms. I don't want 5, I want as many as I have vertices. So this is now, well, I guess we can just take from this get length, put that in there. Get rid of this one. Now I have 9 random Booleans. I grab a mask list, feed these vertices into here, and then this list of Booleans is going to dictate which vertices make it through. So all false will disappear and all true will remain. If we look at this, boom, we only have 4 because there were only 4 trues in that Boolean list. I'm going to move this over. Now we use this list instead. So plug that into the instances. There are only 4, and then this list goes into the locations, and we have our initial seed. We can change this seed in the random Booleans to get a different configuration, and we can also create a bigger grid like so. Oh, that's kind of cool. But I'm going to keep it at 3 for now, and this at 0 for now, and clean this up a little bit. Let's implement Conway's game of life. You can do this all specifically with animation nodes, and I'm sure that would be beautiful for you, but we're going to do it with a simple script node. We're going to use Python because the script node exists for a reason, and we should use it when it's the right thing to use. So I'm going to grab a script node. Script node, this is essentially a way of making a custom node, which is really cool. And the Python is fun, and if you don't know it, you should learn it because it's totally cool. I'm going to call this script Conway, and I will create a new text file, and you can open the text file one of 2 ways. You can click this magnifying glass and then click where you want it to show up, here for example. Another way to do that would be to just open a new window, go to text editor, click here on the drop down and find Conway. Same thing. Join areas, close that down. First, let's create a new output. What I want is a list of lists. Each list within the list is going to be the configuration of live cells for that frame. Okay? So we have 250 frames in this animation at this point, which means our output is going to be a list of 250 lists, each with a configuration. Actually, it'll be 251, including 0. Anyway, the first thing we should do is reduce this number to like 1, because when you're programming, you want your problem to be small when you're figuring it out, so then once you've solved it, you can scale it up. So now we're going to get a list of lists, which is going to be a generic list. And let's get so this kind of just defines the script node, but our actual script node is going to be Conway. I'll put that there, and we'll hook this up to the viewer. And the list is of length 0. And we can output a different list by coming in here and, well, let's name this locations by frame. Be sure not to put any spaces in here. Use underscores because we're using Python now, and a variable needs to be all one word. If I go in here, locations by frame equals this empty list. Go back up here. I'm going to press N. You can trigger this to run by either changing the frame or a property or something in the tree. You can also execute the node tree like so. And nothing's changed because this is an empty list. But I don't want it to be an empty list. I want to test it, so I'm going to create a list of the words hello and world. Let's execute this node tree, and nothing is happening. Why is nothing happening? Well, we look at here. This says locations by frame not initialized. Use default. What? If I look up here, I misspelled locations by frame by saying location by frame. You're going to run into these problems all throughout. So figuring out what went wrong is essential to your workflow. I'm going to execute that node tree again. That warning goes away, and our list contains hello and world. Cool. Get out of here. We don't want you anymore. Get out of here. Oh, also, I'm going to say you want to save your text file separately from your blend file. So I'm going to save this as Conway tutorial, like so. Great. Now the very first list I want to be the starting locations. So I want to append something like locations by frame dot append starting locations. But what is starting locations? It's not a thing yet. We need to add a new input. Vector 2D list. This will be our starting locations. Okay? Now let's input our starting locations, which, if you'll remember, is this masked list that gives us these 4 locations. Put that into our starting locations, and this shows us a list of length 1, which is a single list, and within that list we have our 4 starting locations. Booyah, we're on a roll. Let's start manipulating this with something kind of easy. So we'll get something like next locations equals, and just as an example, we can say this list is just one vector 0, 0, something like this, okay? So on frame 0, we'll have our Tetris piece, and then on the next locations, we want just the center piece. This is just as an example of what is going on here. And notice when I call this vector, you need 2 sets of parentheses, because vector really only takes 1 argument, and that 1 argument is this tuple of the coordinates. So we'll take our locations by frame and append next locations. And now if I go back, we have 2 things in our list. The first list, which is these 4 locations, and the second list, which is just this single location. Does this make sense so far? We're just appending lists within this list. Now, if I go to the second frame, you would expect to see it, but no, you wouldn't, because we're not using these locations by frame in our tree yet. Let's implement that. Move these over. Get rid of this length. Now we want the length of the list for the frame. So we need the frame. We need to know what frame we're on. And we need to get the list by frame. So we'll get list element, and we will put this list in here, and we will look and debug this. Connect this here, and we can see we're getting the first list. If I up the index, we're getting the second list, and we want to control this index by the frame. Move this down here, and now as we go back and forth, we're getting different lists. Beautiful. Beautimish. Move this over here. Now we want to use this list length as our instances. Notice that this is not giving us a list length node because we're using a generic list, and animation nodes is confused. So I'm going to cancel that. I'm going to get Control A, length, get list length, close that down, shorten that up, put this here, put this here. All right, now we've got our 4 again. And instead of using these original locations, which are the locations we expect because we're on frame 0, we're going to use these locations. And it breaks because, again, we're getting a convert node, and we don't want to convert to a vector. We want to convert to a vector 2D list. And that is going to give us what we want and what we need. So if I go to the next frame, we get what we expect. And if we go to the third frame, nothing is there because we only have 1 frame in the animation, and the node isn't telling us what the list should be. Let's continue on in developing Conway. Great. There's light right in my eye. Right now, we're only appending a second list of locations, and we don't want to manually append lists of locations for however many frames because that is terrible. So instead, we'll get rid of this. We need to know what the end frame is. End frame equals bpy.data.scenes 0.frame end. Just trust me on this, okay? Just trust me. For I in range end frame, this is now going to loop 1 time because end frame is 1, and end frame is 1 because our end frame is 1. If I were to up this to 2, this will now loop 2 times, and so on. We want our current frames. So as we loop through, the first time that this loops, I is going to be 0. And then once it becomes 2, this is going to stop looping altogether because 2 is now our end frame. I'm going to get the current frames. Not current frames. Current locations. And that is going to be locations by frame I. So this first time, I will be 0, which is going to get us these starting locations, the first thing in our list. And let's get a next locations equals an empty list. We're going to fill out this next locations as the loop goes, and then we're going to append that to our locations by frame when all is said and done. we need to loop through our locations, our 4 locations here. So for loc in current locations, now we need to loop through the neighbors of each location and assign and iterate a value. So what I'm going to do is I'm going to start here on this location, and then I'm going to look at each of my neighbors, and I'm going to tell them, hey, you have a neighbor. So this location is going to get iterated 1. This location is going to get iterated 1, and so on and so forth. But I need a place to store that information, so I'm going to create a dictionary. Neighbor counts equals curly braces, which is going to give us a new dictionary. And in order to get those neighbor locations, I need to do a little bit of math on this location. I need the offsets. So I'm going to create a list of offsets. Neighbor offsets equals this list of vectors. Vector -1, -1, comma. I'm going to copy and 1, 2, 3, 4, 5, 6, 7, 8. I'm going to copy and paste those, okay? So this offset is -1 on the x, -1 on the y. Then this one is -1 on the x, 0 on the y, -1, 1, and so on and so forth. So these are all -1s, and then we've got the 2 zeros in the middle, and we've got the 1s on the right. And on the -1s, we've got a -1, a 0, and a 1. Got a -1 and a 1. Got a -1, a 0, and a 1. These are all of the offsets, and we're going to loop through them. For offset in neighbor offsets, now we can grab the neighbor locations. So a neighbor location equals the location, which is this. This location. This is just for the first iteration, but it's going to copy for every iteration. And then I'm going to add the offset. And that's going to give us this value. So I believe this value is 0, -1. That's going to mean that this plus the offset is going to be -1, -2. So we'll do location plus offset. Great. Now we need to turn this vector into a string so that we can save the count in the dictionary. So we're going to call that a key. We're going to call a function to key neighbor location. And this is actually going to do absolutely nothing because toKey doesn't exist yet. We're going to create that. Def toKey. This is our own function. It's going to take a location, and it's going to return the stringified version. I'm going to stringify the first value, location at 0, plus, comma, plus the stringified version of the second value, location 1. Sorry, that should be square brackets. And this is going to, this essentially, here's a comment. Everything after the hash does not get read. It's just for your own eyes. It's going to look something like this. 0.0, comma, 0.0. That string. And that is our unique identifier for this particular location, for example. me erase these. Can I? Oh, wow. Okay. No. Oh, cool. Okay. Cool. Now we've got our unique identifier. We're going to check to see that if it's not in the dictionary, if not key in neighbor counts, then we're going to add it to the dictionary. We're going to initialize that key as 0. Neighbor counts equals, nope, sorry, neighbor counts key equals 0. And then immediately iterate on that. So neighbor counts key plus 1. Great. Now we are telling all of our neighbors, hey, you've got a neighbor, you've got a neighbor, you've got a neighbor. And we've collected, let's put a comment here, count neighbors. Great. Next, we want to handle our live cells. This is where the magic happens. Once we know our neighbors, we can live or die by them. So handle lives cubes. Let's call them cubes, not cells. They're cubes because we're in Blender. For location in current locations, just like our loop above, same loop essentially, we need to get our key based on the location, and we're going to check to see if that key is in the dictionary. If key in neighbor counts, why wouldn't, I'm going to pass on that. Why wouldn't the key be in the neighbor counts? I mean, obviously, like, all of these are touching each other, and they are telling the dictionary, hey, I've got a neighbor, and it's this thing. But if you look over here and say we have, like, 5, and this is broken for some reason. Why is this broken? Go over here. List index out of range on line 21. Line 21. Index out of range. What if we just go here? Okay. So I just for simplicity, I've made the end frame 1. We don't need to. Oh, I know why that's broken, but it's because we're not appending more things to the locations by frame. So by the time we get to the second iteration of the loop, there is nothing there because we're not appending new things. Anyway, this will not show up in the dictionary because this is empty, and this is empty, and this is empty, and this is empty, and this is empty. And none of them are telling the dictionary, hey, I've got a neighbor, because it doesn't have any neighbors. So you can assume that if the key isn't in the neighbor counts dictionary, that it has 0 neighbors. Just food for thought. This is why we write this to kind of protect ourselves. Let's go here. Clean that up. Okay, so if the key is in the neighbor counts, then let's grab the count equals neighbor counts key. And remember the rule, if a living cell, which is what we're looking at, has 2 or 3 neighbors, it lives on. So if count equals 2 or count equals 3, then the next locations dot append this location. Okay? Otherwise, we just won't add this location and it won't be in the next locations and it'll die. Very important here, I want to remove this location from the dictionary, because the next time I want to loop through all of the dead cells and not the live cells. So I'm going to say neighbor counts dot pop key. This is going to make sure that we don't deal with live cell locations again. Next, let's handle the dead cubes. So we loop over the keys for key in neighbor counts. We know that, once again, there are only dead locations in the neighbor counts because we've removed all the live locations. For the dead cubes or cells, the number of neighbors has to be 3 for it to come back to life. Grab the count again. Neighbor counts key. If count equals 3, then next locations dot append what? We don't have the location. We need to derive the location from the key. So we'll do loc equals from key instead of to key, and pass in the location. Great. Just like to key, that doesn't exist. So we need to define from key. Pass in a key, and I'm going to use loc equals key dot split on the comma, which is going to return a list of strings. It's going to look like something like this. String of 0, 0, comma, string of 0 dot 0. This is an example of the center cube. And before we return this, we want to turn these strings back into floats. So I'm going to return it like this. Vector float loc 0 float loc 1. And I'm going to close up these. There's 3 parens at the end there, and that should do it for us. That should return a vector with float values instead of strings, and we append that. Great. Once that is all done, we can take this list of next locations and append it to our locations by frame next locations, and that should do it. That's Conway. Less than 60, less than 100, less than 1,000 lines to put Conway in. Let's see if it works now, though. So we've got our starting locations. We've got our next locations. Oh, that looks good. It actually looks really good. Okay, because this has 3 neighbors. This has 3 neighbors. This has 3 neighbors. This has 2 neighbors, 3 neighbors, 2 neighbors, 3 neighbors, 2 neighbors, 2 neighbors. And yep, exactly what we were expecting. Let's try end frame of 2. Boop, boop. Perfect. Looks like it's working, and it's starting to branch off this initial grid of 9. It just continues on infinitely out of our initial grid. We can up this to, like, I don't know, 10 frames and see how that runs. That looks pretty good. I'm gonna take the frame rate down to a custom, like, just to see it run more slowly, like 6 frames per second. That's cool. Let's up this to like 1,000 frames. Now let's watch this run. Okay, not bad, not bad. And you can play with it. You can add a bunch here, maybe like a 10 by 10 grid. And you can change the seed and stuff if you like, but basically I'm going to run this, and you'll see that it runs terribly slowly. It's running so incredibly slow because every single frame it's calculating the whole 1,000 frames. Each frame, that's too much. The way to fix that is click on your Conway node, go to the item tab, advanced node settings, and you're gonna add the one-time cache. Now, this node is going to calculate all 1,000 frames, but only one time. After it's calculated all 1,000 frames, it's just going to output the same value. It's going to cache the value of all of the lists so it doesn't have to calculate it each time. If we run now, we're getting a really good animation. There's not a lot of lag. Oh, it looks cool. Yeah. Sick. I'll also get rid of this 3D viewer. Yeah. And get rid of these. Okay. 7. Now, one caveat is if you make any changes at all, so for example, you're here and you want this to only be a 3x3 grid, you need to press this clear cache. If you don't press clear cache, you're just going to get the old values because all of the values are cache and it's not recalculating. But if you clear cache and then you start playing it, you'll see you've got your 3x3 grid starting position again. So any changes you make sure to hit clear cache so that it updates. And one last thing, if you have like a grid, like a, I don't know, 10 by 10 grid, and you've cleared the cache and it's playing, and you're like, that's cool, but I want to see something else, you can change the seed in the random booleans. Clear the cache, run it, and you'll have a completely different pattern. That's it, folks. Conway's Game of Life in Blender with animation nodes in a script node. Use that Python, figure out how to make really cool shit. Comment down below. Let me know if you enjoyed this, if you want to share any script nodes that you've created. That would be super cool. Hey, if you like what you saw today, please like, subscribe, hit that notification bell.